Okay, so now we come to the last factor, which is temperature. Remember that because our equilibrium constant is temperature dependent, so their values will vary with temperature. All right, so if we consider this equilibrium, right, uh, we know that the enthalpy change is negative. So what will happen if temperature is increased? When temperature increases, all right, our equilibrium will shift to the left towards the endodermic to absorb the heat. All right, and we will have more of the reactants and less of the product. Okay, our Kc will decrease because it shifted left. All right, observation, because our nitrogen dioxide is brown in color, we will see the gas turning brown. All right, this is actually a very classical example for students to observe. All right, so if you go to YouTube, you probably well, anyway, you're already in YouTube, you'll probably be able to Google this nitrogen dioxide equilibrium, all right, experiment. Okay, so when temperature decreases, equilibrium will shift to the right, and then it has more product, yes, and less reactant. Okay, so the Kc will increase because equilibrium shifted right, and the observation is that the color of the brown gas fades. All right, so now we consider this reaction. Okay, so we note that this reaction is actually endodermic. All right, it means that the forward reaction actually absorbs heat, and the reverse backward reaction releases heat. So when temperature increases, equilibrium will shift to the right, and then you have more products, less reactant, Kc will increase. Okay, so the corresponding opposite will happen for temperature decrease. Okay, so forward reaction is endodermic, right? The question is, why does Kc increases? All right, because the rate is faster for both forward and backward, but the forward reaction increases more than the backward. So overall, right, your Kc would actually increases. Okay, so the explanation for why Kc decrease for exothermic reactions, right, is roughly the same, right? So if you read through, you understand it. Okay, application of chemical equilibrium is applied to a Haber process. I think you might have seen this particular example before. Okay, so we need to adjust the equilibrium such that we get the best yield in the shortest time possible. All right, so the operating conditions are actually high temperature, high pressure, beg your pardon, moderate temperature, and the use of a catalyst. Okay, high pressure, right, actually causes the equilibrium to shift to the right. All right, but we cannot use like 1 million ATM, right, because that will result in very, very high cost, because your pipes then will have to be very thick, all right, to sustain the pressure without bursting. All right, temperature, low temperature will give a higher yield, but if too low, then you will have a very, very slow reaction. Okay, catalysts basically just increase the rate of reaction so we can use it. Okay, the final yield is about 30%. Okay, to link your Gibbs free energy to position of equilibrium, if your Gibbs free energy is less than 0, forward reaction is spontaneous. So we can deduce that your Kc is going to be much greater than 1. All right, if your delta G equals to 0, the system is in dynamic equilibrium. All right, and this is a very important equation. right? Because it links your delta G to your equilibrium constant. Okay, so if delta G is more than 0, then the reaction is not spontaneous. Kc will be smaller than 1. Okay, so the summary, basically, you can read through it on your own, is basically what we have discussed so far. All right. Okay, so that's it for your chemical equilibrium. I hope you have caught the gist of it. In our next videos, we will be sharing on the solution of your MCQ. So stay tuned, and I'll see you there.